Okay. So in the last video, kind of what we ended up with is we said, well, if we want to solve this PDE, right, heat equation, homogeneous boundary conditions, initial condition, what we can do is, right, express F, or initial condition, in this way, and then take this expression for each of these terms, tack on this exponential, and then we're going to get a solution. Okay. So what we're going to do now is figure out how to compute what these b sub n are so that we can write out this expression. So there are two ways of kind of thinking of this. They're more or less equivalent, but one is maybe more computationally focused. The other is more kind of generally linear algebraic focused, you might say. But we have two ways of how to actually get these coefficients b sub n. So one feature is we use these integration tricks or techniques or observations, manipulate things, and then notice that we can isolate each of these b sub n. Another way to think of this is that, well, let's think of these sine functions as basis vectors for some space of functions, right? In practice, it turns out that these kind of this set of basis vectors, as you take infinitely many of these sine terms, do form a basis for kind of almost all the functions you care about on an interval. But we're going to use the set of basis vectors, they're functions, but we'll call them vectors. And what we want to do is project our function f onto this basis of sines, cosines, things like that. And so in practice, how we do this projection is via this integration integration approach, but there may be two conceptually slightly different ways of thinking of this problem. Okay. So for one, right, recall one up here is handy feature of trig integrals. Okay. The trig integral will primarily be using or evaluating is this thing right here. Okay. And the fact is that, well, whatever this integral is, it only depends on n and m. Okay. So if n and m, these coefficients here, are different, then this integral is 0. If n and m are the same, then this integral is going to be L over 2, or physically, it's going to be half the length of the interval you care about. Okay. So maybe a picture of the first one is, right, so maybe we have 2 pi, it's pi, so this is sine of, I guess this should be L and L over 2. This is going to be sine of n, sine of pi over Lx. And so what we can do is take another function, but double the period, or I guess half the period. I don't know. The picture I have in mind is the following. That and then that. So then this orange is going to be sine of 2 pi over Lx. Okay. Right, so here when x is L over 2, so plugging L over 2 there, we get sine of pi, which is 0. Right. Maybe I'm off by a factor. Let's see. Yeah, okay, so the picture, thank you for your patience. The picture should actually be, this is sine of pi over L. And then this is sine of 2 pi over L x, right? Because here, right, so when x is equal to L over 2, we're going to get sine of pi over L times L over 2, which is sine of pi over 2, which is, right, a quarter of the way along the sine curve. And so then that's going to be kind of the peak. Sine is equal to 1 there. So we have that. Oop. Otherwise here, right, sine of 2 pi over L times x. So when x is equal to L, we have sine of 2 pi, which is 0. Okay. When x is equal to L over 2, we have sine of 2 pi over L times L over 2. So sine of pi. And that's kind of the halfway point in the picture, and that's also 0. Okay. Yeah. So the observation is, right, for when n and m are different, kind of the picture that we draw is that this kind of the profile for one of these sine curves is going to kind of, right, be positive in a way for half of kind of one of these sections for the other curve. And it's going to be negative for the exact same area for the same section of that curve. Okay. So if you take this product of orange with red kind of here, that's going to give you one value. And then if you take the product of this thing in here with this area right there, that's going to give you a different value, or that's going to give you the same value but negative. Add those up for the integral, you get 0. Okay. So maybe another way to state this is, if your trig functions are oscillating at different frequencies and you evaluate this integral over an entire period for those frequencies, you're going to get 0 because they're oscillating at, you know, comparable or proportional frequencies. And so then if you look in there, things are going to cancel out. So that's maybe a picture way to see this. You can also see this just by computing this integral. Okay. And so we'll say in a second how to get this integral, or give some direction for how you might go about computing this. But how do we use that for kind of what we're interested in with these PDEs? Okay. So we're going to make use of this fact, right, this integral. And so we're going to use it in the following way. And I say, assuming all operations are valid, we're going to be distributing an integral across an infinite summation. We're going to be distributing a function across an infinite summation. So here we're going to assume all the operations we're doing are valid, which they are, but okay. So we would like this to be true, right? We would like to write our initial condition as in this way, or a general function in this way. And the question are, what are these b sub n? So what we're going to do first is we're going to multiply both sides by sine of m pi over L times x. Okay. And so here we can just multiply these two together. The assumption here is that, so technically we have this sum in here times this piece right there. And so what we're going to do is distribute this piece over here across this infinite summation. Okay, so we're left with the sum over n equals 1 up to infinity of b sub n times sine of n pi over Lx times sine of m pi over Lx. cool. And so now what we're going to do is we're going to integrate. Okay. Again, you can think of this as, right, we know what some of these integrals are. We want to make use of this identity. So let's force that into play. So if we integrate this side from 0 to L dx, we end up with exactly this. We're also going to integrate this other side, 0 to L dx, of everything in here. And so now the operation that we're assuming is valid is, right, this integral, we're going to move into the summation. But then we're left with something like this. So this integral, we don't necessarily know. If we were told what f was, we may be able to compute it, but otherwise this is just some integral. Okay? It's equal to the sum over these coefficients b sub n of these integrals. But these integrals we know how to compute. Right, so these were 0 if m is different to n, and L over 2 if m is equal to n. Okay. So the observation is that almost all of these integrals are going to be 0, right? Because if you sum from n equals 1 up to infinity, you say, well, right, n is 1, does it match with m? N is 2, doesn't match with m. N is 3, doesn't match with m. Most of the time, your answer is going to be no. So most of the time, these integrals are going to be 0. Okay. So if we plug that in, right, most of these integrals are 0 except when n is equal to m. Okay. So this summation that we're doing right here, the only term that kind of survives this whole summation is when n is equal to m. So we end up with b sub m. And then when n is equal to m, this integrand in here becomes sine squared of m pi over lx. And well, we actually know how to do this integral, right? This is exactly L over 2 because m is equal to n. So then in the end, what we get is this coefficient b sub m is equal to, so b sub m times this integral, which is L over 2, is equal to this integral, which if we knew what f was, we could compute. Okay. So we end up with this condition. And we're interested in b sub m. So in the end, we can take this, move it over. We get that b sub m is equal to 2 over L times that integral. Or physically, b sub m is equal to 1 over half the length of the interval times this integral. Okay. And so that's our systematic way of computing what these b sub m are if we're given a function f. So these b sub m, these are going to be called Fourier coefficients. I can write it out. So Fourier, that's how you pronounce his name. He's French. Hopefully it's close enough, but it's Fourier. This is the name of the scientist that popularized and really showed why these coefficients are viable and why we should care about them. And so these were named in his honor. Okay, so yeah, great. So now we know how to compute them. I mean, the question is from a linear algebraic perspective, right? What are we really dealing with? So generally, we say two functions are orthogonal, right? Not just vectors, but functions now. We say two functions are orthogonal if the integral of their product is 0. Okay. And so this is, I mean, equivalent thing would be to say these functions are perpendicular, right? We're borrowing the geometric words and geometric motivation, but applying it to functions. Okay. And so what we can also do is use the same sort of expression to define the notion of a size or a norm of a function. And in this case, the norm is going to be, so the norm of a function f is going to be the square root of this integral of the function squared over that interval. So where is this coming from? Well, one motivation is coming from vector norms. Okay. So generally we say two vectors are orthogonal if they're dot product, right? Which for three-dimensional vectors takes this form. You take the x coordinate of each vector, multiply them together, add it to the y coordinate of each vector, multiply together, plus the z coordinate, multiply together. We say two vectors are orthogonal if their dot product is 0. Okay, and then their vector norm is just kind of the square root of kind of v dotted with itself. So then the connection here is that v dotted with w, right, sure behaves a whole lot like, and so I'm going to use a slightly different notation, right? So here, v and w are vectors. So for this dot product notation, we're using instead this angle bracket notation. But this means vi wi, say in 3 dimensions, I equals 1 up to 3. So the observation is that this behaves a whole lot like integral from 0 to L of f of x, say f1 of x, f2 of x dx. Okay. The key properties we want from this dot product is that it's linear in each argument. Okay. And what you can do is you can check that this integral is linear in each argument as well. So we refer to this thing right here as an inner product or dot product for functions, similar to the dot product for vectors. And to kind of drive that analogy home, this integral right here, we would also express as inner product of f1 and f2. And so then the norm of a vector, we can write it as the square root of the inner product of v with itself. Likewise, the norm of a function, we can write as the square root of the norm of that, or the inner product of that function with itself. Okay. Where if we write this out coming from that, we're going to get exactly this expression here. Okay. But it's just one way to think slightly geometrically about the space of functions, right? We're assigning a notion of size, we're assigning a notion of inner product and way of kind of comparing and projecting functions onto another. And so, right, when we're computing these coefficients b sub n, really what we're doing is we're projecting or computing the inner product of a function f with one of these sine functions. But we'll talk more about that in chapter 3.